In Module 3, Lesson 4, we're going to write our sums as products and products as sums. And this is an extension of what we did in Lesson 3. So in Exercise 1, we have expanded expressions, and we're going to have to contract them. We're going to rewrite the expressions as a product of two factors. And in order to do that, we'll need to take a factor out of each of the terms. So we need to look at the terms and we need to find a common factor. In the first expression in A, 72 times t plus 8, 8 does go into 72. So we're going to factor out the 8. And then inside the parentheses, we're going to put the number that we multiply 8 by to get 72, which is 9. And of course, the t remains. Keep our plus sign, and then the number that we multiply 8 by to get 8, which is 1. Now let's complete the same process for each one. 36z plus 72. There are a lot of factors that are in common, but I do know that 36 goes into 72, so I'll use the greatest common factor, which is 36, times 1z or z. Keep our plus sign there. And 36 times 2 is 72. So 36 times z plus 2 will give us the expanded expression. The next one, this is letter E, 3r plus 3s. The common factor is clearly 3, and 3 times r plus s is our contracted expression. 55a plus 11. We know 11 is the common factor. We're not trying to trick you on these things. 11 times 5a will give you 55a, plus 11 times 1, and we can't forget about that 1. It's very important to our expression. And then finally, in the last one, letter D, there's a little bit of tricky stuff going on here. First of all, 15 doesn't go into 144. And since I know 5 doesn't go in there, I would suggest that 3 is probably our common factor. We can check that through the rules of divisibility. And divisibility by 3, the rule is add up the digits in the number. And if that number is divisible by 3, then so is the larger number. So 1 plus 4 is 9. And 9 is divisible by 3. That tells us then the common factor is 3. And then what we'll need to do is actually divide 144 by 3, which will be 48 Q. And we're going to need that subtraction sign. So that's tricky there too. You've got to watch that. And 3 times 5 is 15. And there it is. In exercise 2, we're going to write the product and some of the expressions that are represented in this rectangular array, which is not pre-printed in the student materials. So the sum of the expressions, first of all, is 2x plus 12y plus 8. And we're thinking backwards because, of course, we don't know what those numbers were to start. The first thing we could do is factor out a 2, since 2 goes into each of those terms. So if we did that, that would mean that this would be 2. 2 times x is x. 2 times 6y will give you 12y. And 2 times 4 will give you 8. So when we rewrite that expression, we would have 2 times x plus 6y plus 4. And the rectangular array helped us to factor a little easier this first time around, and maybe a few more times around. In part B, we're asked to factor 48j plus 60k plus 24 by finding the greatest common factor of the terms. So we need to know what the greatest common factor of 48, 60, and 24 is. For the benefit of some who have not done Euclid's algorithm, I'm going to suggest to you, by doing it myself, that we find the greatest common factor with the Euclid's algorithm. And in that, we'll divide the largest number by the smallest number and continue until we find 0 as our remainder. So if I divide 60 by 24, I know that that goes in twice, which is 48, leaving us with a remainder of 12. Then we'll continue the same pattern by dividing the divisor, that's the number outside, by the remainder until there is a remainder of 0. So we go 24 inside, 12 outside, and 12 goes into 24 2 times with no remainder. And when we get no remainder, we know that that number, the divisor of that problem, is the greatest common factor. So now that we have the greatest common factor, what we'll do then is factor it out. 12 is our greatest common factor, and 12 times 4 12 times 4j is 48j. And 12 times 5k will give us 60k. And 12 times 2 will give us 24. In example 3, we have a variety of different expressions written all different ways, and we're going to write each sum as a product of 2 factors. And we need to especially look at the distributive property. So first of all, 2 times 3 plus 5 times 3, our common factor in these two multiplication problems is 3. So we can factor out the 3, and 3 is being multiplied by both 2 and 5. Now, to justify equivalency, what we want to do is actually solve. So 2 times 3 is 6, plus 5 times 3 is 15, and that's equal to 21. Looking in the expression that we wrote, 2 times 5 is 7, and 3 times 7 is 21. So they are equivalent. Next one. We have 2 plus 5 plus 2 plus 5 plus 2 plus 5. So this expression is repeated addition, and we repeated the addition 3 times. So we can write 3 times 2 plus 5. Interestingly enough, same thing as we saw in the first one. 3 times 2 plus 5 is 21, and if we add everything together, that's 7 plus 7 plus 7, which equals 21. In the third one, very interesting problem we have here. We have 2 times 2 plus 5 plus 2 plus 5 times 2. Since we have these terms being added together, please notice the parentheses, and then of course multiplication happens first anyway. We could group the 2 times 2, put grouping symbols around them because that doesn't change anything when we put grouping symbols around a multiplication problem. And then, since each of these terms in the parentheses is being added, we can, any order, any grouping, we can move this 5 times 2 through the commutative property next to the 2 times 2. So let's rewrite 2 times 2 plus 5 times 2 plus 5 plus 2. All right, and once these are next to each other, we can see that there's a common factor of 2 in these two terms. So we can actually factor that for these two terms, and that would be 2 times 2 plus 5. And then don't forget to tack on our last 5 plus 2 problem. Now, hopefully at this point, we can see that there is a very common thing going on. Inside the parentheses, we have 2 plus 5, or 5 plus 2. And since we're adding any order, any grouping, we can go ahead and change our second term. We could always change the first one as well, but I'm going to change the second parentheses term into 2 plus 5. So now we have 2 times 2 plus 5 plus another 2 plus 5. And that's actually 3 times 2 plus 5. 2 of those and then one more. That's 3 times 2 plus 5. Let's check it to prove. 3 times 2 plus 5 is 21. Let's go up to our original expression, which was 2 times 2, which is 4, plus 5 plus 2, which is 7, plus 5 times 2, which is 10. And 4 plus 7 is 11, plus 10 more is 21. They're equivalent. Let's look at expression D. We have x times 3 plus 5 times 3. Our common factor is 3, so if we factor that out, we have 3 times x plus 5. Three times x plus 5. Next one, x plus 5 plus x plus 5 plus x plus 5. Well, we clearly have 3 repeated additions of x plus 5. And in F, we have 2x plus 5 plus x plus 5 times 2. Well, we're adding these terms together, so we can move this. Let's go ahead and put grouping symbols around the 5 times 2, because multiplication happens before addition anyway, but it will show that that's happening first. And now we have three terms that are being added together. But since this is multiplication and this is multiplication, let's go ahead and use the commutative property to move things around a little bit. It's a little bit harder on the computer. When I can't use the multiplication symbol there. Okay. So now what we have is 2 times x plus 5 times 2 plus 5 plus x. Well, a common factor between these two terms is a 2. So if I factor out a 2, I would have x plus 5, and then plus 5 plus x. And we know from our previous problem up above that we could rewrite this 5 plus x as x plus 5, and then it would look very much like our other term. And then, of course, now we have 2 times x plus 5 plus another x plus 5, and that is 3 times x plus 5. And then in our last row, one more time, we have a common factor of 3. So this would be 3 times x plus y. And then, of course, in the middle, 3 times x plus y. And finally, in our last, let's go ahead and move the 2x plus 2y near each other. And then y plus x, although I'm probably going to change the order there. We can factor out a 2 in these first two terms. So we'd go 2 times x plus y, and then add the y plus x, but let's use the commutative property and change the order of those two terms, since we can clearly see that it's the same as the first. And then, just like we did in the others, we have 3 x plus y terms, so 3 times x plus y. Next, in example 4, we have a real-world problem. A new miniature golf arcade opened up in town. And for convenient ordering, a play package is available to purchase. It includes 2 rounds of golf and 20 arcade tokens, plus $3 off. There's a group of 6 friends purchasing this package, and we're going to let G represent the cost of a round of golf, and T represent the cost of a token. We're going to write 2 different expressions that represent this total amount for the group, and explain how the expression describes the situation in a different way. So let's label first. We have G equals the rounds of golf, and T represents the cost of a token, too small there. And then our package was 2 rounds of golf, 2G, plus 20 arcade tokens, 20T, plus $3 off. And $3 off will be represented with a -3. There are 6 friends that are going to purchase this package. 2 rounds of golf, 20 arcade tokens, and $3 off. We're going to write 2 different expressions. We just wrote one. Now, in order for us to write a second one, we could factor out a 2 for these first two terms. So let's go ahead and do that. 2 times g plus 2 times 10 is 20t. And then add the minus 3. Now that's for each person. And so now what we would need to do is multiply this whole thing times 6. Okay, and then if we expand it, which I think would be a little easier for us on the top expression, if we expanded it, 6 times 2g is 12g, plus 6 times 20t is 120t, plus 6 times negative 3, which is negative 18. There we have two different expressions that show it two different ways. This one shows how much each person will owe and then multiplies times the number of people. And this one shows how much the total group will spend. Now in exercise 5, we're going to look at what the opposite of negative 6v plus 1 is. Keeping in mind that we show the opposite by making a negative sign in front of the whole expression. The opposite of negative sign means the opposite of negative 6v plus 1. Now when I put that negative sign in front, it really means to take everything inside the parentheses and make it its opposite. So each term then is going to be the opposite. The opposite of negative 6v is positive 6v. And then the opposite of positive 1 is negative 1. You'll also see that written frequently as 6v minus 1. So start to get used to writing it yourself. Then in part B, they ask us, using the distributive property, to write an equivalent expression for part A, which is what we just did. We wrote it this way, and then we wrote the equivalent expression. Example 6, we're going to rewrite 5a minus the quantity a minus 3b in standard form and justify each step applying the rules for subtracting and the distributive property. So the first thing we want to do then is rewrite all the subtraction as addition. We have 5a plus, and now we have to take the opposite of each of the terms inside the parentheses. That's what that minus sign in front of it means. So we're going to have negative a plus, and the opposite of minus 3. Well, let's go back. Negative a. Matter of fact, let's not even do that subtraction yet. Let's keep that subtraction, and let's change the subtraction inside the parentheses first. We have a, changing this to addition, we'll add the opposite, so plus negative 3b. Okay, then our next step. We have 5a, now we're going to change this subtraction to addition. and the term after the subtraction sign. And the term, please notice the term after the subtraction sign is the whole term in parentheses. So everything inside the parentheses has to change. So we're changing this to plus negative a. Remember, we're doing the opposite of everything that's there. Plus the opposite of negative 3b is positive 3b. And finally, if we have any like terms, which we do, we have 5a plus a negative a. So if we take 1a away from 5a, we end up with 4a. And there are no common terms for b, so 3b. Let's practice that some more in exercise 6. We're going to expand each expression and collect the like terms. So we'll multiply negative 3 times each term inside the parentheses. Negative 3 times 2p is negative 6p. And then let me go back up and rewrite this term inside the parentheses as addition so we can see that. Negative 3 times 2p plus the opposite of 3q, which is negative 3q, because that will help. Then we'll multiply. Negative 3 times 2p is negative 6p plus negative 3 times negative 3q is 9q, positive 9q. Okay? And in 6b, again, we have, wow, lots of negative signs here. So let's change the subtraction inside the parentheses first. Keep everything else the same, negative a minus. We're going to do a plus the opposite of b, which is negative b. Okay. And then we're going to apply this subtraction as well. So that's going to become negative a plus the opposite of a, which is negative a, plus the opposite of negative b, which is positive b. Then finally, we're going to collect the like terms. There are, let's see if we can get a little more space here. There are 2 negative a's. So that is negative 2a. Plus 1b, and there it is, negative 2a plus b. Remember when you're practicing to rewrite your subtraction as addition, because at this point in your understanding, it's probably very easy to make some pretty big mistakes otherwise.